do start when you can.
All right. Thank you. So it's a pleasure to talk about my work today. So I've been working on this project roughly for the past year with my supervisor Juan as part of my PhD. So this will be relatively a short talk with minimal equation on screen. So hopefully everyone in the audience can follow with my talk. So to start with, I'm going to be giving a bit of motivation for my work. So as we know, models of isolated system can be a good approximation for real-world celestial objects and can be used for applications of GR. So then one needs a reliable description of isolated system. And one way to do that is to look at the asymptotic behavior of the gravitational field in an isolated system. So to study the asymptotic behavior, the key idea is usually to bring points at infinity to a finite distance using a conformal transformation. Then one can either study the behavior of fields at large null separation, and in this case we have the notion of asymptotic simplicity, which identifies spacetime, similar to Minkowski as we approach null infinity. Then we can look at the asymptotic behavior of fields at large spatial distances. However, if in a standard point compactification of spacetime, spatial infinity is represented as a singular point, and studying the asymptotic behavior of the gravitational field is challenging because of this singularity. So there are different approaches to address this singularity, but our focus in my project was comparing Friedrich construction of the cylinder at spatial infinity, which can be used for the discussion of the initial value problem, and Ashtekar notion of asymptotic flatness at spatial infinity, which combat the fact that the definition of asymptotic simplicity does not describe the behavior of gravitational field at spatial infinity. So just to give a brief outline of the slides to follow, so I will be initially talking about the different representation of spatial infinity in Minkowski as a simple example of the two different approaches of Ashtekar and Friedrich. Then I mentioned the central definition that our work is based on, which is Ashtekar's definition of the asymptote at spatial infinity. And then I will also discuss briefly how we can relate these construction in general spacetime, and also mention briefly the construction of the conformal Gaussian system. So in this case, what I mean by general spacetime is spacetime that satisfy Ashtekar definition, which we'll be giving later in this talk. So first, we have the well-known point compactification of Minkowski, which follows by making use of double null coordinates to compactify spacetime into a region of the Einstein cylinder. In this case, we have the usual different subset of the conformal boundaries. So we have future and past null infinity. We have also the future and past time-like infinity points. And finally, we have the spatial infinity point. Now, for spacetimes other than Minkowski, specifically spacetime with non-vanishing ADA mass, this representation of spatial infinity has issue. So in particular, the initial data for different gravitational fields diverge at this point. So this representation is not suited for studying the asymptotic behavior of the gravitational field near spatial infinity. So then to go to the cylinder, the construction of the cylinder at spatial infinity, I'm not going to be going into the details of the construction. However, I'm going to look at a graphical representation of the point compactification compared to the cylinder at spatial infinity. So here we have a plane, the ρ and t plane, and we have the spatial point infinity is brought to the origin. We have the usual null boundaries, future and past null infinity. Then by introducing a change in the time coordinate from t to tau, the Friedrich time coordinate in Minkowski, this point, the point of spatial infinity, can be blown into a cylinder, which is represented in this diagram by an interval I. And we also have the two critical sets, I plus and R minus, where the null infinity meets the cylinder at spatial infinity. So also here we have the blue lines of constant ρ. These are So lines of constant flow in this metric represent solutions to the conformal geodesic equations. There are non-intersecting congruence of solutions. And we later make use of these solutions to construct a Friedrich cylinder near spatial infinity for a metric that satisfies Ashtekar definition, which will be mentioned later in the talk. So then for the case of Ashtekar construction, spatial infinity is blown up to a time like a three-dimensional hyperboloid that acts as a boundary of the spacetime. An Ashtekar hyperboloid can be visualized in the tau rho plane. So here tau and rho are just the Friedrich coordinate in Minkowski. So one thing to note here is that these hyperboloids and Ashtekar coordinates never reach the null boundaries. So Ashtekar construction in this way cannot be used to study the structure of null infinity. And this is also one of the issues that we address in our definition for the spacetime metric when we look at relating the two constructions for general spacetimes. Initially, what we did is looked at relating the Ashtekar and Friedrich construction in Minkowski so that we can use this as a guide for a more general spacetime. So in the case of Minkowski, we're able to find an explicit conformal relation between the three-dimensional metric unit hyperboloid and the metric of the spatial infinity. Then if we define the spacetime metric using our three-dimensional metric and also the unit normals, we can also directly link the neighborhoods of the cylinder and the hyperboloid at spatial infinity through a coordinate transformation and a conformal transformation. Then in the second part of our project, we specifically considered spacetime that satisfy Ashtekar definition. So it's necessary to mention the definition here in my talk. So Ashtekar gives this definition of the asymptote H, or the asymptote at infinity, which is a boundary H for the manifold M. And then we also define a smooth function omega on M, which would satisfy some conditions. So specifically, omega should be 0, and its derivative should not be equal to 0 on H. And more importantly, Ashtekar defined the metric on the hypersurface of constant omega and the normal in such a way so that they admit a smooth limit as we go to H. So also these spacetimes, so we can say that these spacetimes are asymptotically flat at spatial infinity if the topology of H is that of a cylinder, okay? So then using this definition, we have an associated conformal gauge freedom. So if we have M and omega satisfy an Ashtekar definition, then we can also define this omega prime, which is just alpha omega, where alpha is constant on H. And in this case, this would also satisfy the definition of Ashtekar. Then we can also drive some condition for that physical field that are satisfied on H. So specifically, we can directly show that the three-dimensional Ricci tensor is proportional to the 3 metric on H. And we can also show that the electric and magnetic parts of the Weil tensor are, their limit is equal to 0 as we go to H. Now, in order to relate the construction of the cylinder at spatial infinity, as we did in Minkowski, we first look at relating the three-dimensional metric. So since the definition of Ashtekar is quite general, we can't give an explicit conformal relation between Q, which is a metric of the hyperboloid or the asymptote, and the cylinder of spatial infinity. However, we can prove this proposition so that the metric Q of an asymptote H satisfying Ashtekar definition is conformally related to the standard metric of this Friedrich cylinder. Then, if we want to link the metrics in the neighborhood of spatial infinity, we can define our spacetime metric in such a way to solve 2 issues. First, as I mentioned, we have that the hyperboloids of Ashtekar don't reach the null boundary. So we initially we introduced a compactified version of the metric for the asymptote so that allow us to reach the null boundary. We also, our spacetime metric has a singularity. So we have to define a frame in which the various fields, including the metric, the connection coefficient, and the Shelton tensor are regular at H. Since our choice of the spacetime metric on H coincide with the metric of the cylinder at spatial infinity, we can make use of the solution of the conformal geodesic equation on the cylinder to construct a conformal Gaussian system. And then using stability argument, we can show that the solution also can, for the conformal Gaussian, can be extended out of H to a neighborhood in a neighborhood of H, and then that is used to construct a Gaussian system in the neighborhood of H, which in turn can be used to construct a Friedrich cylinder near spatial infinity. To summarize, first, what we looked at is Minkowski spacetime, and we found an explicit conformal relation between the hyperboloid at spatial infinity and the cylinder at spatial infinity. Then also for general spacetime metric, we showed that the three-dimensional metric satisfying Ashtekar definition is conformal to the metric of Friedrich cylinder. Then giving a metric that satisfies Ashtekar definition, we show that we construct a conformal Gaussian system near spatial infinity, which gives rise to a Friedrich representation of spatial infinity in a neighborhood of the asymptote H. This is the end of my talk. I don't know if we have any questions, and thanks for listening.
So many thanks for your talk. Does anyone have any comments or question? Jacek? No?
Perhaps I want to comment that when you are saying that the electric and magnetic part of the Weil tensor vanishes at spatial infinity, perhaps it is true, but it depends where are the indices, etc. Because there is some important physical information in this data at infinity, namely the mass, angular momentum, etc. So if we think about asymptotically flat initial, not initial, but asymptotically flat space-time at spatial infinity, we should see for instance, the black hole or whatever. But this is the comment. Maybe nothing is wrong in this presentation.
Okay. All right. Thank you.
Well, if I may, another comment. Of course, this Ashtekar business is a variation upon a construction of Bike and Schmidt, which was perhaps actually even more detailed than what Ashtekar did. So it's worth mentioning in this context.
Yes, yeah.
Right. Further questions or comments? So if no, many thanks.
So maybe I could ask a question to Helmut, if there's been any progress on where Scry meets the cylinder using the. I mean, one should be able to extract this from the Hinz-Vashi methods, right? Any new thoughts on that, Helmut, or have you heard about this? You are muted, so you have to open your microphone.
It's open?
Oh, yeah.
No, I don't see anything new in this. And I'm slightly surprised about some points. For example, the last point on the last slide. I always thought Friedrich's representation is based on conformal geodesic. Now they do something. I have no idea where this conformal Gauss system comes from they talk about.
So we have a solution for the conformal geodesic on the asymptote. So the conformal geodesic equation, and then we prove that these solution can be extended of the asymptote. So then we can construct the conformal Gaussian system in this way.
I'm surprised. I mean, I always thought these Ashtekar hypersurface, they, coming back to the first picture you showed us, they become tangent to Scry at the end.
Yeah. So this is so. Yeah. So I mean,
I mean, you have conformal geodesics on these hypersurfaces?
So what I'm saying is that what we do is actually we redefine the space-time metric so that the part that coincide at spatial infinity is just the cylinder, the metric of the cylinders at spatial infinity. So we redefine the space metric and we use Ashtekar definition in this way. So we redefine the coordinates and the space-time metric.
You take the picture with the cylinder, and then in that framework you discuss Ashtekar's construction.
So for Minkowski, we didn't redo the. I guess we didn't redefine the space-time metric. So what we've done that for a general space-time. But initially, as I said, we looked just at Ashtekar construction as it is, but then we did, as I said, redefinition of how the space-time is defined for Ashtekar.
Mm-hmm. I never understood.
So that first we remove the singularity because there obviously Ashtekar what he does is for the space-time metric specifically. So he rescale the metric for the asymptote or the hyperboloid differently from the normal. So and then if we want to scale it the same with the same factor, then we have a singularity in the normal part. So then we use like coordinate transformation to remove this singularity so that we have I guess a regular metric that as we go to infinity. So again, when we go to infinity, our metric is actually just the metric of the cylinder.
Maybe we should better have a coffee in the common room or in Vienna and then talk about that.
Yeah, okay, all right.
Great. So I guess Vincent, Mariem, for your talk. And